Hello. In this presentation, we'll do a simple example of hierarchical use of transformations in 3-space, specifically for a solar system example. This is very similar to the example in section 2.3.2 in the textbook. It's also traditionally one of the assignments used in Math 155A, particularly project number 2, so it's very close to that as well. So let's start by, what we're going to do for this is we're going to render a simple solar system with a sun and an earth and a moon around the earth, and we're going to have various parameters that control the placement of these. So let me start by drawing the x and z axes. So the x-axis goes this way as usual, but we're going to use a top view where we're looking down onto the solar system, and let the z-axis be this way. So the sun will be centered at the origin. Here's where the origin is. The y-axis is coming out of the board towards you as viewer, and the solar system is going to lie entirely in the xz plane, and we're looking at it from the top. So the sun is at the middle. Here's the sun. And the sun is going to be rendered as a sphere of radius 1. And the earth is going to be placed distance r sub e, radius sub e, so it's going to be distance r sub e from the sun. So the earth will sit here. It's going to make an angle theta sub e, its placement with the z-axis. So I think if the earth has moved out distance r sub e at an angle theta sub e from the z-axis, and we're also going to rotate the earth on its axis due to, say, rotation during the day. So we're going to rotate, phi will be the rotation of the earth on its axis. And the moon will get placed somewhere over here, and the distance from the center of the earth to the center of the moon will be r sub m. And if you extend the line out from the center of the sun through the center of the earth, that makes angle theta sub m with the direction out to the moon. So here's the moon. And we're going to render the earth with a sphere of radius 0.7, and we'll render the moon with a sphere of radius 0.4. So these are not to scale with the solar system by any means, but it's just a way of illustrating the properties here. And we're going to render all three of those things using a sphere S, which is a sphere of radius 1, centered at the origin. So we can just use S for the sun, because the sun will also be rendered as a sphere of radius 1 centered at the origin. And so you'll notice that we have these various parameters here. The parameters that we're going to use are, there's theta sub e and r sub e that give the position of the center of the earth, phi, which is the rotation amount of the earth, and then there's theta sub m and r sub m, which give the position of the moon relative to the position of the earth. And it's going to be the case that the phi, which controls the rotation of the earth, is not going to affect the position of the moon. So we're going to set the code up so that happens. In other words, earth is spinning on its axis, making days. The moon is going around at a more leisurely rate. It's not affected in our model by the spin of the earth. It's just got its own angle, theta sub m, that is independent of phi. So let's draw some pseudocode here. Write some pseudocode here. So this will be the kind of thing that gets translated later into OpenGL code, but we're just going to do it at a sort of mathematical level here. And I'm going to be using a bunch of matrices. And I'll use these matrices as model matrices that transform the position of the sphere S to put the sun, the moon, and the earth in the appropriate place in the scene when they're rendered. So the first step in the pseudocode is I'll set ms equal to the identity. And then we'll render the sun here. I'm not going to I'll say this in English. Render m sub s of s to render the sun. And what I mean by this notation is S is the sphere of unit 1, of radius 1 centered at the origin. We transform it by the identity matrix, which of course doesn't change it at all, m sub s, and then we render it as the thing at the center. Right? Okay. Now that's finished rendering the sun. That was easy. So now let's talk about rendering the Earth. So we need a matrix for the Earth. So I'm going to use two of them. First of all, m0, I'm going to start off by making it equal to ms, but I'm going to multiply it by a rotation matrix that does the rotation phi sub e here. And we'll look at the order of this a little later. So r theta sub e comma j. So this is going to be to rotate around the sun. Or I should, more properly, I should say revolve around the sun. So this is the transformation that's going to revolve it around the Earth around the sun. And we're using r with rotation, with angle theta sub e, with the right-hand rule rotating around the j-axis. So remember the right-hand rule rotating around the j-axis, we grab onto the j-axis with our right hand. The curl of the fingers gives us the direction of the rotation. And so, in fact, that is the way that theta e is measured. And then, so we notice we came off of ms. So ms controlled the placement of the sun. So this way, if the sun were to move, the Earth would follow it. And then we have another me0 is equal to me0 times the translation transformation 0, 0, re. So this is what moves the Earth away from the sun. So we think of moving the Earth away from the sun, this and out. So let me write this out, and then let's go back to this and see why this makes sense. And then we use another matrix, me1, which is going to be equal to set to me0 times r phi j. And this is going to rotate the Earth on its axis. So we went from me0 to me1. We're saving me0 to use that later on with the moon. And so this rotates the Earth on its axis. And we also want to shrink the size of the Earth. So me1 is then multiplied by, on the right, by scaling of 0.7. So this shrinks the Earth by a factor of 0.7 to make it into a smaller sphere. And then we render, at this point, we render m sub e1 of the unit sphere to render the Earth. Okay, so in other words, we're using me1 as the model matrix. We're taking the unit sphere, which is sitting center at the origin, we're transforming it by me1, and we're getting this. So I've been calling these matrices all along. You can either think of those transformations with composition, but we're going to use matrices to represent these things. So they're really 4x4 matrices acting on homogeneous coordinates, and we're just doing matrix multiplication to compose these things. So now we still need to render the moon. So we're going to now set m sub m, a brand new matrix, is equal to me0 times r theta m j. So this is going to revolve the moon around the Earth. So we're using the angle theta sub m, which is the amount that the moon is revolved around the Earth. We're using the j-axis to revolve around. Again, right-hand rule tells us that gives us the right direction of rotation. We now need to move the moon away from the Earth. So we set m sub m equals m sub m times t sub 0, 0 rm. What this is doing is it's moving the moon, distance r sub m, away from the Earth along the direction of the z-axis. Now, this is going to be affected by the previous operation that revolves around the Earth. So we're pushing the moon away from the Earth in the direction of the z-axis, but that's affected both by the revolution of the Earth, of the moon around the Earth by angle theta m, will also be affected by the revolution of the Earth around the Sun by angle theta e, and so the overall translation direction will end up reflecting those other rotations. And finally, we need to scale m sub m colon equals m sub m times s 0.4, which scales the sphere, or the moon, by a factor of 0.4. And finally, we render m sub m of the unit sphere to render the moon. So what this will mean in our OpenGL program is we're going to render the unit sphere, but we're going to have a model matrix that transforms the unit sphere to move it to the correct position and to shrink, including shrinking it down. So this is the pseudocode that'll generate the positions of these things. So I'll break this down a little bit more in a moment, but just to notice right now, we have m sub e0 placed the Earth in the right position, but it didn't get affected by the revolution of the Earth on its axis, the rotation of the Earth on its axis, and it didn't get affected by the scaling. The moon started with m sub e0, so thus the moon was not affected by the Earth spinning on its axis and not affected by the scaling of the Earth. So the moon's position is then affected by rotation, translation, but not this rotation, scaling, and then by another rotation, another translation, and then by scaling. All those things work together to affect the position of the moon. So let's break this down some more and understand how this m sub e1 manages to place the moon at the correct position in the solar system. So let me start by just selectively erasing it. More will get erased in a moment. When we do the rendering right here, m sub e1 is equal to what? Well, we started with the identity matrix. We multiplied by r theta ej. So it's r theta e j. We then multiplied on the right by t sub 0, 0 re, translating along the z-axis. We then rotated by phi, that's r phi, around the axis j, and then we scaled by s 0.7. So this is the matrix, that's the active model matrix, when rendering the Earth. The Earth is being rendered as a sphere of size 1 centered at the origin, but it's being transformed by this matrix. So let's see, I'm going to redraw this picture now. Let's see what this does to the Earth placement in the solar system. So here's our x-axis. Here's our z-axis pointing down. We're still in a top view. And we're going to think about how these transformations that are multiplied together act on the Earth. So, or in particular, act on S. So we start off with S is the unit sphere centered at the origin. Now, when we think of these things acting on S, remember we're taking this whole thing applied to S. So if we think about it step by step, we're taking the scaling applied to S, we're applying r phi to that, t sub 0, 0 re to that, and then finally r sub theta ej to that. So let's just take this step by step. If you take the Earth and shrink it, different color, make a blue Earth for a moment. Here's the sphere of radius 0.7, and that's what happened if we just took the scaling and applied it to the Earth, okay, to the unit sphere. That's shrinking down the Earth. Now let's suppose that, let me draw something on here. Suppose that San Diego was sitting right here on the Earth. If we shrink it down, San Diego is sitting there. If we do the rotation, right, by phi, San Diego will be sitting here. So after we rotate, we're going to get the sphere, again, of radius, the same sphere of radius 0.7, except rotated by the angle phi. So this is the angle phi here. When we apply r phi j, think of taking that blue sphere and moving it to where the red sphere is. Exactly the same position of sphere, but rotated around the y-axis. So now that's the effect of, if we took r sub phi j times s sub 0.7 of the sphere. Now we think of applying the translation. The translation is sending us distance r sub e down the z-axis because we're adding on 0, 0, re. So what that does is it takes us down. So we do a translation 0, 0, re. And now we end up with the sphere sitting right here. Here's still San Diego. And here's the center sitting on the z-axis down distance re. And when we apply the translation, those three matrices multiply together, apply to S, put it here, still a radius 0.7. Now we rotate. Rotate means rotate around the origin through angle theta e. Rotation axis is the j-axis. The direction is given by the right-hand rule. So this would take us then by r theta ej, would take the sphere and place it here. So this would be the angle theta e. This would still be radius 0.7. It would still have the rotation on its axis of angle phi, and would place the Earth in the correct position. Now, the moon is going to do something more complicated. The moon, we have multiple steps here. We get a snapshot of that. I'm going to go a little quicker on the moon and not show as much detail on this, but m sub m at the very end, it's going to be the same first two things, r theta ej times t sub 0, 0, re, but then we're using E0 times r theta m j times t sub 0, 0, rm times s sub 0.4. These are the transformations that are applied to the moon. When we render the sphere, I'll just run through these steps very quickly and let you feel in the details. We think of starting off with a unit sphere S. We scale it down by 0.4. We translate it down distance rm. We rotate by theta m around the j-axis. We translate it down by 0, 0, re. And we rotate the whole thing. Here's the origin here. We rotate from the origin by angle theta e. And then the moon is placed there in the appropriate size and so forth. This is the final position of the moon. So these are the steps that we can think of these transformations applying to the moon to render it in the correct place as well. So I want to end up by giving you a sample of what the code would actually look like in your C++ program to do this. The mathematics is like this, and you may have wondered, why did I do all these single step things? I multiplied by a rotation, and I multiplied by a translation, and why did I do that one step at a time? It's because the C++ commands that are typically used in OpenGL do these things just one step at a time. It's also tends to be a more efficient way to do the computation. So let me just, however, write you some OpenGL code that corresponds to the first part of this program here. So again, it's not going to be completely clean OpenGL code, so I'll call it, it's sort of OpenGL code, sort of C++ code for OpenGL. And it's using the linear math routines that I'm providing for the course. So there's many different math routines available you can use, but this is the ones I've written for this course follow the original OpenGL commands pretty closely. And I'm going to mix it in with some math symbols as well. So the first thing is I'll say m sub s, I'll use this as if it were a variable name, we'll just say set identity. So this takes the matrix M sub S and makes it into the identity matrix. So this is a 4x4 matrix for homogeneous equations, which is the identity matrix. 1's on the diagonal and 0's everywhere else. Now at this point, we render M sub S of S. I'm not going to write the OpenGL code for that at the moment. And then we set M sub E0 equal to M sub S. We have an extra step here because I don't have a command in the code just for that kind of thing. And then we multiply it by M sub 0 dot mult, this is the member function, underscore GL rotate theta E 0, 1, 0. So 0, 1, 0 here, this is like the vector J. So the mult GL rotate says multiply by the rotation matrix, which takes a rotation of angle theta E around the axis 0, 1, 0. And then we have ME0 dot mult GL translate 0, 0, R sub E. And this multiplies the matrix M sub E0 by the translation matrix, which translates by the amount 0, 0, R sub E. And then we do M sub E1 equals M sub E0. We make a copy explicitly. And then we do M sub E1 equals mult GL rotate. Now we're on this line here, phi 0, 1, 0. So again, we're rotating around the y-axis. The rotation axis is 0, 1, 0. And we're rotating by angle phi. And then ME1 is, whoops, there's too many equal signs here. These should have been dots. I'm sorry about this. No, this is equals. This should have been a dot. So now ME1 dot mult GL scale 0.7. So this is multiplying by the matrix that scales by 0.7. This is the 4x4 matrix that has zeros everywhere, but the diagonal has 0.7, 0.7, 0.7, 1. The bottom row is 0, 0, 0, 1. And then finally we render the Earth. Render M sub E1 of S. In other words, we render the unit sphere using M sub E1 as the model matrix, or the model view matrix. And then we do something similar for the Earth, for the Moon. Similar code for the Moon. Okay, so when you're implementing the solar programming project, you'll be doing this kind of coding to put together your transformations, your rotations, your scalings, and your translations. All right, that's all for this presentation. Thank you very much.